So in the previous lecture, we were discussing examples of Fourier series, and essentially we discussed this theorem regarding convergence of the series. So this result says that whenever the function is continuous, the value of the function at that point equals to the value of the Fourier series at that point, whenever the function is continuous at that point. And whenever the function is not continuous, we'll find left and right limit of the function at that point, and we take the average value. This average value equals to the value of the Fourier series at that point. So let us so continuity we already use, but let us see when the function is discontinuous. So if we see the graph of this function, then the graph we can see that the graph will be on the left side it is 0 value, right? And on the right side the function is x square, and then again it will repeat. So here we will get 0 value, then again it will be x square, right? So because it is a 2 pi periodic function, so this is a point of discontinuity, right? So at this point, so what is this point? This point is basically x equals to pi, right? So since it is a periodic function, f of the function repeats after 2 pi cycle, right? So but f of pi is, if we find f of pi left, then left side of pi we have the value of the function to be x square. So that means it will be approaching to pi square, right? And on the right hand limit of pi will be 0 value, right? Value of the function is 0 because it is 2 pi periodic function. So the value is 0. So that means whenever we have discontinuity, we take average value of this. So at pi, the average value will be pi square by 2. So let us complete this example. So note that,
Sir, set done, sir.
right? So yeah, just let me write down that. So note that the left limit at pi will be pi square by 2. Sorry, pi square, and right limit will be 0. So that means the average value will be pi square by 2. So from the theorem, what we get is, we get this average value, which will be the value of the series at x equals to pi. And we already found the Fourier series. The expression is this one. So I think I have missed pi here. Just verify in the denominator, because here we have in this term, when we multiply here, pi will cancel out. So in the numerator we have pi, but in this term we have pi common, I think. So just verify. I have done some mistake in pi, so that you can rectify. But whenever we substitute pi, we can see that this term will be 0, right? Because sine 2k pi is also 0, and sine 2k minus 1 pi will also be 0. So that means this part will be 0. Only this part will remain in the Fourier series. So whenever x equals to pi, this term will be cos n pi. So let us write down the right hand side, which is pi square by 6 plus summation 1 to infinity minus 1 power n by n square times cosine n pi. And then we know that cosine n pi is minus 1 power n. So this will be nothing but minus 1 power n into minus 1 power n, that is minus 1 power 2n, that is even power of minus 1 will be 1, right? Because cos n pi is minus 1 power n. So now we got this series, and then we take the numbers other side, we get summation n 1 to infinity 1 upon n square is half times pi square by 2 minus pi square by 6, right? Because this 2 number we are taking on the other side, it will give us half. So now if we take LCM, this will be 3 pi minus pi square, so that is 2 pi square by 6, right? And that is essentially pi square by 6, and the left hand side series is 1 upon n square and 1 to infinity, right? So depending on whether the function is continuous at that point or not, we can find the Fourier series at that point, and whenever the series is convergent and divergent, the condition is given in the theorem. Okay, so today we want to discuss a new topic, that is Laplace transform. So let us start with the definition of that. So Laplace transform is one of the way to solve differential equations, and in particular initial value problems. So let us see first of all what is the definition of Laplace transform. So let f be a function defined on closed interval 0 to infinity to r, be a function. So for such a function, we define the Laplace transform denoted by L of the function ft is defined as integral 0 to infinity, right? Because domain is 0 to infinity, e power minus st ft dt, right? So s is some real number, and small f is the given function. So we define for given function this integral, which is known as Laplace transform of the function f, whenever this integral exists. So exists means the integral is finite, it is not infinite number. All right, so this is just a definition. We are given some function f, we will find this integral, that is a Laplace transform. And note that the Laplace transform is a function of, so it not only depend on the t variable, because now we have integrated with respect to t, so it is only function of s, right? So it is a function of s variable, right? So we use the notation. So it is function of s, and that function is corresponding to small f function. So we use the notation f of s for the same quantity. So 0 to infinity e power minus st ft dt, we also denote by a function of s variable. So we will see some example, it will be more clear after that. So this is just basically the notation, and we further use notation. So basically the Laplace, this is Laplace transform of small f function, and that is f of s. So that means we also use the notation ft to be nothing but Laplace inverse of capital Fs function. So now it is a bit difficult to understand this notation, but let us see one example. It will be more clear. So the simplest example is polynomial kind of functions. So find Laplace transform of t power n, where n is a positive integer, right? So we want to find Laplace transform of t power n. So that means our function is, given function is ft is equals to t power n, right? So we want to find Laplace transform of t power n. So let us use directly the definition of Laplace transform. So Laplace transform of f is by definition integral 0 to infinity e power minus st ft dt, and ft we know that the given function is t power n dt. Now we want to integrate this integration from 0 to infinity, so we straight away integrate the integral and substitute the limit. So if we straight away integrate this function by integration by parts, then we can see that if we use integration by parts and differentiate this function, then we can get a new integral in terms of t power n minus 1, that is in the derivative of t power n. So let us use the integration by parts. So t power n as it is, integration of e power minus st is e power minus st divided by minus s, right? So here we will require to divide by the number s. That means essentially we are finding the Laplace transform for numbers other than 0, right? Because if s is 0, we can't divide by s. So we are finding for s greater than 0. And the second term of the integration by parts is derivative of t power n, that is n times t power n minus 1 times integration of e power minus st. Now when we substitute the limit, we have already taken that s is a positive number. So whenever s is a positive number, e power, when we substitute infinity, e power minus st will be 0, right? And whenever we substitute t is equals to 0, this term will be 0. That means this whole term will vanish when we substitute the limits, right? The first term will cancel out, only the second term will remain, that is n divided by s, because minus minus will become positive, integral 0 to infinity e power minus st e power n minus 1 dt. So what we have done here is we wanted to find Laplace transform of t power n, and what is this quantity? This is basically e power minus st times this function. So what is this function? The function is basically e power n minus 1. So this term is Laplace transform of t power n minus 1. So what we proved is, we proved that Laplace transform of t power n is n divided by s times Laplace transform of one less power, right? So now we can use this iteratively. So let us write down shortly. So what we get is, we get Laplace transform of t power n is n divided by s Laplace transform of t power n minus 1. So using this, yes, any doubt?
Second, last for this chapter, our first term is disappeared.
Yeah,
Vanished.
that is because s is positive number, right? So when s is a positive number, uh, what will be this term when we substitute t is infinity?
One upon minus one upon s.
Yeah, so basically e power minus s times infinity, and s is positive.
Yes, sir.
So what will be this value?
Uh, 0.
That will be 0, right? So this term will be 0 at t is equals to infinity, and when t is 0, t power n term will be 0,
Yes, sir.
right? So the difference will be 0 in that case,
Yes, sir. Understood.
right? So the first term will vanish, and when we substitute the limits, and yeah, so we are getting this iterative term, so that we can use iteratively. So the Laplace transform of t power n we are getting in terms of t power n minus 1, t power n. Same formula we can use for n is equals to n minus 1. So we get Laplace transform of n minus 1 in terms of t power n minus 2. So using this repeatedly, so we shall get the Laplace transform of t power n is equals to, so we will use n times. So that means we get first term will get n by s, second term we get n minus 1 by s, and so on. So we get n minus 1, n minus 2 up to 1. So that is n factorial divided by s power n. And finally we get Laplace transform of one function if t is equals to constant function 1. Right, basically we are using this formula iteratively. And then we need to find what is Laplace transform of constant function 1. So that is n factorial by s power n, and Laplace transform of 1 is e power minus st times 1 dt. So this is a simple function to integrate. So that is integral of e power minus st is e power minus st by minus s 0 to infinity, right? And when we substitute this limit, again the same thing we will use. If s is positive, so e power minus s times infinity is 0, and when we substitute 0, minus minus will be plus, and e power 0 is 1, so we get 1 upon s, right? So essentially final answer will be n factorial divided by s power n plus 1. So what is Laplace transform of 1? Laplace transform of 1 is 1 by s, and the Laplace transform of t power n is n factorial divided by s power n plus 1. So let us write down this finally. So what we proved is Laplace transform of t power n is n factorial divided by s power n plus 1, right? So now we can see, now we can understand the notation that whenever we find Laplace transform of function of t, we are getting function of s, right? So this function is function of s, and that corresponding to ft function, so we will denote it by capital fs function, right? And in terms of, in other notation, or in other words, we will also use for the same formula Laplace inverse of n factorial by s power n plus 1 is nothing but t power n. Right? So whenever we have Laplace transform of t power n is this function, its inverse is this function. That is this notation. Right? So for simple functions, we can find Laplace transform in this way. So let us see some more basic examples. So the simplest example is, what is the Laplace transform of e power at? Right? So whenever we find Laplace transform of this function, this is our ft function. So just substitute 0 to infinity e power minus st times ft dt. So combining the power of e, we will get e power a minus s t dt. Now this number is, the integral depends on the given number is positive or negative, right? So using that, we will assume that if s is greater than a, then the number is s is greater than a, so this is negative number, right? So in this case, if we integrate, what shall we get? We get e power a minus st divided by a minus s, and the limit is from 0 to infinity. Yeah, so whenever the number is negative and we substitute infinity limit, it turns out to be 0, right? Again, it is like e power minus infinity type of term. So the first term, when we substitute t is infinity, it will be 0, and when we substitute 0 term, it will be minus 1 by a minus s times e power a minus s times 0. So that will be nothing but, this will be 1, so it is 1 upon s minus a, right? So basically what we are using here, because s is greater than a, so s minus a is positive. Yeah, so what we proved that Laplace transform of e power at is 1 upon s minus a, and we use the condition s is greater than a. And in other notation, so this is basically, again, this is a function of s, and in the other notation, Laplace inverse of the function of s is function of t. Yeah, so similarly we can find Laplace transform of cosine and sine functions. So let us find first for Laplace transform of cosine at function, where we are taking, yeah, so here straight away we will apply the Laplace formula. So Laplace formula of cosine at is equals to integration 0 to infinity e power minus st cosine at dt. So again, now we will apply the integration by parts formula. So when we use integration by parts formula, we will integrate the term e minus st and differentiate the cosine term. So the first term we'll get is cosine at time e power minus st divided by minus s 0 to infinity minus integral 0 to infinity. The derivative of cosine 80 is minus a times sine 80 times the second function integral, that is e power minus st divided by minus s dt. So now we substitute limit, then this term e power minus st will be 0 at infinity, and when we substitute 0, so e power minus st will be 1 and that term will be minus, so cos 0 is 1, e power minus st is also 1 divided by minus s, minus when we further use the integration by parts, then the integral will be a sine 80 divided by s e power minus st divided by minus s. The limit is 0 to infinity, right? So first term is as it is. We have integrated e power minus st again, so we get this term. The second term will be minus minus plus 0 to infinity, differentiating sine 80 again, so we get a square cosine 80 divided by s e power minus st by minus s. So just verify whether we have done any mistake or not. So we use integration by part formula once again, and now again we can see that we have not mentioned s is greater than 0, but we are dividing by s everywhere. So that means we need that condition, s should be greater than 0, right? Otherwise we cannot divide by s. So that is the condition, and finally what shall we get when we, this term will be 0 because at infinity e power minus st is 0 and sine is 0 whenever t is 0, right? So we get 1 upon s plus a square by a square, this will be minus, and what else we get? We get cosine 80 integral. So let us rewrite as e power minus st times cosine 80 dt. So now you can see that what is this function? This is nothing but the Laplace transform of cosine 80, right? So Laplace transform of cosine 80, when we applied integration by parts 2 times, we got the 1 upon s times Laplace transform of cosine 80, right? So we can take this term on the other side. So what we got is, we got Laplace transform of cosine 80 is equals to Laplace transform of cosine 80 into a square by s square. So when we add, we get 1 plus a square by s square, that is, so let us write down one more term for more clarity, is 1 upon s, right? So this term we have taken on the other side, so it became positive. So now if we take LCM, this will be s square plus a square by s square, and then that term we can take on the other side, so we get cosine 80 is equals to s will, one s will be cancelled out, so essentially we get s divided by a square plus a square. So using integration by parts 2 times, we got Laplace transform of cosine 80 in terms of Laplace transform of cosine 80, and then we have made the term in terms of Laplace transform of cosine at t by combining the terms, and that way we derived the Laplace transform, right? So in other notation, again in the inverse notation, we get L inverse of s divided by a square plus s square is cosine at. So basically, this inverse notation will require when we will discuss the solution of differential equation using the Laplace transform. So now we know that how to find Laplace transform of function in terms of t to get the corresponding function in terms of s. So there is certain theorem in this Laplace transform which are easy to derive. The first result is known as first shifting theorem. So in which we will shift the s variable. What this says that if we find Laplace transform of function of t, so that we know that it is a function of s, right? And that function will denote by capital Fs corresponding to small fs. So whenever we have Laplace transform of given function f, which we find, and in that corresponding function, if we substitute s minus a, then this function is a Laplace transform of e power at times the original function, right? And in other words, the Laplace inverse notation gives this formula. So Laplace of this function is this function, then inverse of this function is this. That is this notation. So basically we want to prove this formula using the given equation. So let us start with the f of s minus a. So what is f of s minus a? F of s minus a is the Laplace transform by substituting s minus a instead of s. So that means basically we get so Laplace transform is this formula, but now we need to substitute instead of s minus a. So that means we get this formula, right? And when we substitute s minus a instead of s in the Laplace transform, if we convert into the original Laplace transform, we are getting excess term here. So the first term is e power minus st times e power at ft dt, right? So this is an essential term which comes along the ft function. So if you combine both these terms, then this is a Laplace transform of this function, right? Laplace transform of this function. So if we rewrite in terms of Laplace transform, this is Laplace transform of e power at times ft. So that is what we wanted to prove. Laplace transform of the given function, when we substitute s minus a, we get Laplace transform of e power at into ft. So let us see some applications of this result, simple applications. So we know Laplace transform of standard functions like e power nt, cosine nt, and yeah, so So we found for cosine 80 function. Similarly, we can find for Laplace transform of sine 80, and Laplace transform of sine 80 is nothing but, instead of s divided by s square plus a square, we have a divided by s square plus a square. Let me use some other color for, yeah. So Laplace transform of sine 80 is a divided by a square plus a square. So what is a? A is the given constant, which is a multiple of t in the cosine 80, and s is the variable which is defined, which is used to define the Laplace transform. Okay, so let us take one example of the shifting theorem. So find Laplace transform of e power at cosine wt. So w is some fixed number. So here we can see that in first shifting theorem we are getting Laplace transform of function multiplied by e power some number times t. So whenever we want to find Laplace transform of the function times e power at, we will use the first shifting theorem. So here in this example, we can see that we know the Laplace transform of cosine wt, but that is multiplied with e power at. So that we will use this first shifting theorem. So we know that Laplace transform of cosine wt is s divided by s square plus omega square, right? So if you see this formula, what is Laplace transform of cosine 80? That is s divided by this square plus s square. So here a is omega or w. So just substituting a is equals to w, we get this formula. Okay, and then so what is this? This is basically f of s, capital Fs. So using the first, okay, so this capital Fs where we are taking small ft to be cosine wt, right? So the Laplace transform of this function is f of s, that is this function, and using the first shifting theorem, we get f of s minus a to be Laplace transform of e power at times ft. So let us substitute. We know fs. So f of s minus a is nothing but, instead of s we need to substitute s minus a divided by s minus a square plus w square is equals to Laplace transform of e power at times ft. What is ft? Ft is cosine wt, right? So we got this formula. So whenever we know Laplace transform of some function which is multiplied by e power at, we need to just substitute instead of s minus a in the Laplace transform formula. So in the other notation, the inverse of s minus a divided by s minus a square plus w square is this function, right? So this is regarding the first shifting theorem. Similarly, there are other applications of the direct application of the Laplace formula. So we have the Laplace transform function, which is function of s, that is defined from 0 to infinity e power minus st ft dt, right? So this is a function of s. We have already observed that whenever we find Laplace transform of any function, we get function of s, right? So this is the function of s. So if we differentiate this equation, right? So if this is given, then if we differentiate this equation with respect to s variable, what shall we get? We get derivative of fs, that is derivative of the integral, right? So the integral is in terms of t, that means we can take the derivative inside integral, so that is we get derivative of e power minus st function, and the derivative of minus st function will be, we are differentiating with respect to s variable, so we get e power minus st divided by minus t ft dt, right? Sorry, we are not integrating, we are differentiating this time, so we get minus t times e power minus st ft dt. So what does this gives? This gives, if we take minus common, 0 to infinity, this is Laplace transform of the function t times ft, right? So let us write down that this Laplace transform of t times ft. So using this kind of simple computations, we get the formula that Laplace transform of t times ft function is nothing but the negative of derivative of fs, where what is fs? Fs is the Laplace transform of ft function. What is fs? Fs is Laplace transform of ft. And if we use this repeatedly, we get Laplace transform of t power n, that is nothing but nth derivative of fs. So if we know the formula of first derivative, we can find the formula of the nth derivative. So let us take one example and then we'll stop for today lecture. So we want to solve Laplace transform of t times sine at function. So in this example, we can see that we know the Laplace transform of sine at function, that we already found. So that we have not found, but you can check easily because we have found cosine at formula. Similarly, sine at formula we can derive, and that is Laplace transform of sine at is a divided by a square plus a square. So, but we don't know what is Laplace transform of t times sine at. So this formula helps. If we know Laplace transform of ft function, we can find Laplace transform of t times ft, right? So here we take ft is equals to sine at, then the inverse transform of, then we know that Laplace transform of ft is equals to Laplace transform of sine at, which is a divided by a square plus s square, right? So we know Laplace transform of ft, which is basically we use the notation f of s for this. So therefore, from previous theorem, what we know, Laplace transform of tft by formula it is minus the derivative of fs. So this is from the result we discussed just now. So this gives for this particular function ft we get Laplace transform of t times sine at is equals to minus derivative of this function. So this is a function of s which we are differentiating with respect to s, and a is a constant. So now we know the derivative formula of the division, that will give us minus 2sa divided by s square plus a square whole square. Right, just divide this using the derivative formula of f divided by g function. So f dash g minus g dash f upon g square. That will give us this formula. So finally the answer is minus minus plus will give us 2as divided by the denominator square. So in other formula, in terms of inverse, the inverse of, so whenever we have this type of term and we want to find the inverse will be this function. Okay, so I think we can stop here for today lecture.